Hello. Today we're going to talk about solving equations, and it's done basically the same way as solving inequalities. We're going to be solving inequalities, and it's done basically the same way as solving an equation. For instance, we have 2x is greater than 10. It's not 2x equals 10, but we do it the same way. So we're going to put a line down the middle, just like we would have done for an equation. And then we're going to look at our left and right side and see what we need to do to get x all by itself. So the only thing tied up with the x is a 2, and that's 2 times x. So we do the opposite of multiplying and divide. So x is greater than 5. Now, prior to solving inequalities, we solved equations, and the only answer x could be was 5. But now, x can be any number bigger than 5. We don't have an equal to underneath our greater than symbol. It is not this symbol. It's this one. So it doesn't equal 5. So we learned in our inequality videos, the introduction to what they were, that it can't be 5, but it can be any number greater than 5. So we put an open circle on the 5 and shade to the right. Because 6, 7, 8, 9, 10, so forth are all numbers bigger than 5. So any number bigger than 5 makes this inequality true. But as you can see, we did it the same way that we solved an equation. Here's another example. This is like our two-step equations. So for now, we have an inequality. It is less than or equal to. It does have the equal to piece on it. So when we graph it, we're going to use that closed-in dot. We have to solve it before we know how to do that. So in this problem, here is the only term that has an x. So first I want to isolate that by adding 4 to both sides. Then 3x is less than or equal to 14. And now that we've isolated the x term, we'll get x by itself by dividing by 3. So x is less than or equal to 14 over 3. 3 goes into 14 4 times with 2 left over. So that's how I would write it, as a fraction, or it's 4.6 repeating written as a decimal. So because I got a fraction, that's okay. I want to go somewhere between the 4 and 5 and put my closed dot. And since the arrow points to the left, x is less than or equal to 4.6 repeating. Since it is less than, I can know where to shade if my x is on the left-hand side by looking at which way that the inequality is pointing. So it's pointing this direction because it's any number less than 4.6. So 4 is an okay answer. 3, 2, 0, negative 6, negative 9, any of these numbers down here are possible solutions. And even 4.6 repeating, or 4 2/3, is possible because we do have the equal mark underneath our less than. So it's less than that number or equal to it. Here's another example of solving an inequality. Same way we did with solving an equation. In this problem, we have x's on both sides. As I taught you before, I normally take the x that's on the right side and eliminate it from both sides. So I want to subtract 5x here. Do not want to write it underneath the 10 because I want to make sure I line up my like terms. So this is 7x minus 10 is less than 4. And now that I have all my x's on the left-hand side, and that's how I like where I like to put mine. You can move all your x's to the right side, but I like to keep it on the left just to keep things consistent. Here's my term with the x in it, 7x. So I have to move the minus 10 by putting a plus 10 on both sides. Then I have 7x less than 14, and then I divide by 7, and I end up with x less than 2. So all the numbers less than 2 are solutions to this inequality. It can't equal the 2 because this does not say less than or equal to, it just says less than. So I'm going to put an open circle on the 2 and shade it those numbers that are smaller than 2. I can also look at the arrow that's in the problem here that's pointing to the left. So I'm going to shade to the left, but you should also understand that it's because 1 is smaller than 2, 0 is smaller than 2, and all these negative numbers are smaller than 2. But the numbers over here are bigger than 2, and that's why we can't shade them, because they do not make the inequality true. Here's another example of solving an inequality. This time we have some parentheses on the left-hand side, so we have to distribute. So remember, distribute means to take the factor outside and multiply it by both things inside. So 3 has to be multiplied by 2x minus 3 has to be multiplied by 3. It's greater than or equal to 15. So that's 3 times 2 is 6, so that's 6x, and 3 times 3 is 9. So that's minus 9, greater than or equal to 15. Now I know all my x's are on the left side, so I'm going to isolate the x term by adding 9 to both sides. Move this up here, so I had 6x left on the left-hand side. I had a greater than or equal to sign. And then I have 15 plus 9, which is 24. Now to get x completely by itself, I divide by 6. So x is greater than or equal to 4. So with that greater than or equal to 4, that means all the numbers larger than 4, including 4, it is not that symbol, greater than, it's greater than or equal to. So we can actually have 4 as a solution. So we put a closed dot. My arrow here, my inequality is pointing towards the right, where those are the numbers bigger. All the numbers have to be bigger than 4, and that's over here. The number smaller than 4 are on the other side. So all of these numbers are solutions to my inequality. Everything's going well, right? But then we have something happen here when we multiply or divide by a negative number that we need to look out for. We're going to multiply both. 5 is greater than 2, and that's true. It's better to have $5 than it is to have $2. That's better. So 5 is greater than 2. But if I multiply the left side by negative 3, to keep it the same inequality, I got to multiply this side by negative 3. Then I get negative 15 is greater than negative 6. Well, is owing $15 better than owing $6? No, it is not. Negative 15 is not greater than negative 6. It made my inequality not true when I multiplied by the negative. Well, if I simply take my inequality sign and flip it around, now my inequality is still true. On this bottom one, we got divide both sides of the following by negative 2. So I'm going to take this side and divide by negative 2, and this side and divide by negative 2, because we know with equations and inequalities, as long as we do what to one side, what we do to the other, it keeps the inequality true. 12 divided by negative 2 is negative 6. It's greater than negative 4 divided by negative 2 is positive 2. Now we know that having $12 is better than owing $4. That's what a -4 would represent. But then we are saying here that owing $6 is better than having $2, and we know that's not true. But again, we can make the inequality true by simply flipping the inequality sign. Now, math is done by patterns, and once you have a pattern that is true every time, it become a rule for mathematics. So our rule is this. Anytime we multiply or divide by a negative number, we need to flip the sign to make the inequality true. Our inequality is not going to stay true when we multiply or divide by negative. It will for everything else. So we're going to try out some examples for this. So this time we have -4x is less than 12. So in order to solve this, the only thing that need to do to get x by itself all the way is to divide by a -4. That gives us our x by ourselves, and 12 divided by -4 is -3. But our less than symbol, because of the rule, has to be flipped over because we divided by a negative number. Again, the flip happens if you multiply or divide by a negative number. Now x has got to be greater than -3, but it can't equal 3 because the equal part is not there. It's this symbol, not that one. So it has to have an open circle pointing to the right, so those numbers that are larger than -3 are to the right. And just know that only works if our x is on the left-hand side of the inequality. That's why I like keeping x's on the left if possible. It's not always possible, but most of the time it is. All right, now we have this inequality. We have 5x plus 3 greater than or equal to 7x plus 13. Now let me show you a common mistake made by students. Again, I like moving my inequality to where the x's are on the left and my equations. I just like to keep the same rule of thumb. So I'm going to take 7x away. We are subtracting 7x. We are taking 7x away. We are not multiplying by -7. We are not dividing. We are subtracting. Subtracting does not change the inequality sign. So 5x take away 7x is -2x. Then we have our plus 3. This goes away. Still greater than or equal to 13. Inequality symbol did not change because I did not multiply or divide by negative. I subtracted. I'm going to need to subtract again to get this inequality to where the -2x is by itself on the left side and 13 minus 3 is 10. But again, I'd subtracted. The flipping occurs usually in the final step because that's where we're going to multiply or divide to solve. Now, since this is -2x is multiplication, I'm going to divide. Now I have divided by a negative, so that means that inequality sign must be flipped over. I do have this symbol, not this one. So it can equal -5. So I want to close in my dot. My x is on the left-hand side of the inequality. So the arrow, that way the arrow points, is where all my possible answers are. Remember, with an inequality, we have more than one possible answer. We have an infinite. You could sit and name numbers that would work all day long and tomorrow and the next day and forever because it keeps going on forever. So -6, -7, all these numbers on this side are smaller than -5 because it's worse. You're worse off. You're better off to have -5 and you're worse off to have these other things. So they're smaller than -5. And again, like I said, solving an equation is the same thing as solving an inequality. So no matter what we run into, for instance, in this problem, we have a parenthesis on the left and a parenthesis on the right. Remember we talked about covering up one of the sides? So if I wanted to cover up